Because we're not really going to get into the nitty-gritty of the form of the Hamiltonian or anything like that, I'm going to have to ask you to accept at face value this idea that physical systems are indeed governed by the Schrödinger equation that includes the hydrogen atom. The question I'd like to turn to now, though, is what are the products of solving the Schrödinger equation? Why are they useful to chemists? They really are useful, take my word for it. And there are two big things that come out of solving the Schrödinger equation. One is a set of wave functions psi sub I. And the other is a corresponding set of energies E sub I. So for each wave function psi I, there's a corresponding energy E sub I. Now, as we've talked about already, these sets of wave functions and sets of energies are infinite. There are an infinite number of psi i's and ei's that tend upward and upward and upward and upward. However, there is finite spacing between each of the energy levels. For that reason, quantization is found in quantum mechanical models. To represent the psi i's and the ei's, we could, for example, write out the mathematical forms of all of the psi i's. Each one shows us a particular probability distribution, essentially, over all space, the probability of finding the electron at a particular point in space, and the corresponding energy associated with that. But that gets a little bit unwieldy because dealing with the mathematical symbols and stuff makes things hard to interpret. And so chemists more often use a form called an orbital energy diagram. Orbital, by the way, is just a proxy term really for psi I, for the wave function. Orbital and wave function, as far as we're concerned, are synonymous terms. An orbital energy diagram for the hydrogen atom looks something like this. We have a vertical energy axis that runs from negative infinity at the bottom to positive infinity at the top, and the red horizontal lines that you see correspond to energy levels. For the hydrogen atom, these correspond to actually more than one psi I per level, because there's more than one psi I with a particular energy value in the general case. However, I've just drawn it this way to keep things simple. Think of this as a scaffold for electrons. We add electrons to each level to show that that particular electron is characterized by the wave function at that energy level, and you can see its energy visually as being either very stable near the bottom of the diagram or very unstable near the top. And the zero of energy corresponds to separating the proton and electron to an infinite distance. And so low energy means that the electron is, in a sense, bound to the nucleus. As we move to higher energy, the electron moves farther and farther away from the nucleus. Now, one thing to notice immediately is that this diagram explains the discrete wavelengths that we saw in the atomic spectrum of hydrogen way back in the first video. These energy levels are discrete. That means for the electron to change in energy, it has to either jump up or down by a specific amount. It can't jump up or down by any old amount. It needs to move from one energy level to another. And that constrains the wavelengths of light that are emitted. So when an electron jumps down, for example, from the third to the second level, we observe a very specific wavelength and corresponding energy of light. This explains directly the discrete atomic spectra that we observe. Each psi I EI pair within a particular energy level is called an orbital. And there are three important components to any orbital. And really, to wrap your mind around the orbital concept, keep these three properties in mind. The first is the shape, and this is really just the form of psi over all space. Chemists like to use graphical forms of psi. We don't fool around with the mathematical symbols terribly much. We like to use graphical forms of psi, and I'll show you the shape of an orbital and how to think about it here in a second. That's the first property. The second property is the energy. How stable are the electrons in the orbital, usually represented by the letter E. And on an orbital energy diagram, lower energy means more stable electrons, higher energy means less stable electrons. The third property is the occupancy, and for a particular psi and energy value, this can be 0, 1, or 2. To represent that an orbital is occupied on an orbital energy diagram, we use either an up or a down arrow. We can have two electrons in a particular orbital because the electron can either take an up spin or a down spin, so that two electrons of opposite spin can fit into a single orbital. Now you'll notice that the levels here are not equally spaced, but there is a pattern here. the distance between levels is sort of halving as we move upward, and this fits an equation. Namely, the energy of a particular level is equal to 2.18 times 10 to the negative 18 joules times 1 over n squared, where n is exactly this quantum number that we've been seeing. It's an integer that's 1, 2, 3, 4, 5, etc. up to infinity. And notice that when we get to infinity, we are up at the highest energy possible, namely zero energy when the proton and electron have been completely pulled apart. This equation was actually discovered when the atomic spectrum of hydrogen was measured, long before the advent of quantum theory. So it's pretty amazing that by solving the Schrödinger equation, we can actually recover the form of this equation. It's called Rydberg's formula. The other neat thing about the hydrogenic orbitals is that we can use them as a scaffold to predict the electron configurations of heavier atoms as well. All we really need to do is add electrons and think a little bit about orbital energies. We'll talk a little bit about how that works in the next video. But for example, to predict the electron configuration of helium, all we need to do is add another electron to the lowermost orbital of the hydrogenic set of orbitals. So the atomic orbitals of the heavy elements look very similar to those of hydrogen, with just more than one electron as we have for hydrogen.